Welcome to the Chapter 8, Part 3 video, where we'll be looking at our last type of conic section, which is hyperbolas. We are going to be focusing on geometry and translation of hyperbolas, as well as the reflective property of a hyperbola. Why is it important? Hyperbola is the least known conic section, but it's used a lot, again, in astronomy, optics, and navigation. So again, using these is going to be very useful in being able to kind of understand the equations and identify the shape of these equations. So a hyperbola is the set of all points in the plane whose distance from two fixed points in the plane have a constant difference. For an ellipse, they had a constant sum. For a hyperbola, they have a constant difference. The fixed points are the foci of the hyperbola. The line through the foci is called the focal axis, same as an ellipse. The point on the focal axis midway between the foci is the center, same as an ellipse. And the points where the hyperbola intersects with the focal axis are the vertices of the hyperbola, same as an ellipse. So notice the names for all of these parts are the same as an ellipse. However, the difference is that instead of closing in around itself like an ellipse does, a hyperbola is going to open up around the foci, opening away from each other's. So here's an image of a hyperbola. We have our focal axis. That's the line that kind of cuts the hyperbola in half sideways. Then we have two foci, and within those foci are the vertices. For an ellipse, remember we had a focal axis, we had two foci and two vertices, but the vertices were outside of the foci. That was a bad drawing, but you can kind of picture, it's not any better. These were the vertices, these were the foci, and then we still had the center. So the difference here is the vertices are inside of the foci because our hyperbola is opening outward. We still have values A, B, and C. For an ellipse, we found those by the distance from the center to the vertex is A. That's still true. Center to the vertex is A. But now for B, we have a distance from the center. It's going to be the slope of an asymptote. I'm going to talk about that a little bit later. But we can still say that our distance from the center to the focus is C. So center to the vertex is A. Center to the focus is B. And now is C rather. And now we can say that B is kind of our one that's harder to picture. It's going to be the slope of the asymptotes that create our hyperbola, and C is our biggest value. So now we can say that C squared is A squared plus B squared, which is the Pythagorean theorem. Okay. We have our table of values or our table of formulas. If our hyperbola is centered at 0, 0, then we don't have h and k yet. So we have x squared over a squared minus y squared over b squared equals 1. Notice that's an x minus y. So what that means is that our hyperbola is opening sideways. That x is our focal axis. Then we have y squared over a squared minus x squared over b squared means that our hyperbola is opening up and down, where y is our focal axis. Okay, we have the foci and the vertices are the same as an ellipse. And then instead of having a major and minor axis, we have our semi-transverse axis. That's just another word for major. The reason we don't use major and minor is because now our semi-transverse axis could actually be smaller than our semi-conjugate axis, which I think of as the minor axis. So the semi-conjugate axis could be a larger number. B could be bigger than A. However, the roles of like which direction the hyperbola opens, the semi-transverse is the same role as the major axis for an ellipse, and the semi-conjugate is the same as the minor axis for an ellipse. The reason we don't use those words, we're not using the same vocabulary here, is because the semi-transverse axis could be bigger than the semi-conjugate axis, but it could also be smaller. So we can't use major and minor anymore because major would always have to be the bigger one, and A is no longer always bigger than B. Okay, the Pythagorean relation we talked about, I mentioned it on the last slide, and the role of that relationship is that it gives us A and B, which are the slope together, the slope of our asymptotes. So speaking of the asymptotes, we have this image that we can use in order to kind of draw the most accurate hyperbola, is to draw in the asymptotes. So if we think back to the first hyperbola that we learned about, which was the graph of 1 over x, we had two asymptotes and they happened to be the x and y axis, and that gave us the shape of our hyperbola. Same thing goes here, but instead of being axes, we're going to have two not perpendicular lines, but two lines with opposite slopes. So one positive, one negative. Okay. Now that means I could have a hyperbola with asymptotes that are both very steep. And the hyperbola could be either a sideways opening or up and down opening hyperbola. So there's not just kind of a cookie cutter shape for a hyperbola. So I could have something like this, and that would mean that my B value is much larger than my A value, so that the ratio gives me a big slope, a tall slope, right? A steep slope. Okay, so let's look at some examples. First, we want to find the vertices and foci of the hyperbola. So I'm going to remind myself by drawing a quick picture. Find the vertices and foci of the hyperbola. Well, I know that I need this set equal to 1, so I'm going to divide everything by 36. We get x squared over 9 minus y squared over 4 equals 1. I know the center is at 0, 0 because there's no h and k values. This is the center. X is over 9, so I'm going to count out 3 in each direction because 9 is 3 squared. And then y is over 4, so I'm going to look at 2 squared going in the y direction. Now what this gives us is this kind of box. And the box has asymptotes that go through the corners. This is where that slope comes into for our asymptotes. So you might have noticed on the last slide, sometimes it's A over B, sometimes it's B over A. It's going to depend on which variable is underneath X and which one is underneath Y. So our slope was always change in Y over change in X. That's still true. Our Y is 2, our X is 3, so our slopes for these asymptotes are plus or minus 2/3. Okay. So I know my center. I know my vertices will be at A along my focal axis. X was first, so that's going to be here and here. And then I have the shape of my hyperbola. So my vertices are at -3, 0 and 3, 0. For the foci, I need to then look at my A and B values. I know that C squared is A squared plus B squared. A squared was 9, B squared is 4. So that's 13. That means C is the square root of 13. The square root of 13 is between my perfect squares here are 9 and 25. 9, or rather 16 is my next perfect square. So that means the square root of 13 is between 3 and 4. So I'm going to put my foci here and here. Remember, the foci should be outside of the vertices. So that gives us -√13, 0 and square root of 13, 0. foci, and the vertices. I've answered each part of the question, so there is my solution. Let's take a look at another example. In this example, I'm given some critical values and I want to find the equation. So it's backwards from what we just did. Find the equation of the hyperbola with foci, so that means my C value is coming from there, of 0, 4 and 0, -4, whose conjugate axis length, that was the minor axis, has a length of 2. So minor is B, or conjugate is B. If my entire conjugate axis has a length of 2, then my semi-conjugate axis is going to be 2 divided by 2, which means that my B value is 1. Okay, I also know that my C value is my center has to be halfway between my two foci. Center is halfway between 0, 4 and 0, -4. So if I graph this 0, 4, 0, -4, halfway between that center is 0, 0. Now, none of the points that I've drawn so far are actually on my hyperbola. I do know that I have a B value of 1, but what I'm missing is an A value. So I'm going to use my, my Pythagorean relationship. C squared equals A squared plus B squared. C has a distance of 1, 2, 3, 4. You can also get that from the point. 4 squared equals A squared plus B was 1 squared. So that's 16 minus 1 is A squared. A equals the square root of 15, which is going to be just shy of 4. So I can draw kind of my box. There are my asymptotes. The vertices. So I know that the A value is the square root of 15. So now to find the equation, I need to know what variable goes first. Since this is up and down opening, that means the variable that goes first is going to be my y squared over something minus x squared over something equals 1. My distance from the center in the y direction to my vertex is the square root of 15. So we have the square root of 15 squared. And then my distance in the x direction was 1 squared. So I get y squared over 15 minus x squared over 1 is just x squared equals 1. So again, just like we've seen in our last two sections, the key is to solve for the variables. What if our center is not 0, 0? Well, the same thing we've been seeing each time is that we're going to incorporate h and k into our formulas. This is the one that you want on your formula sheet. So our standard equations, now we have x minus h everywhere there was an x, and y minus k everywhere there was a y. Our focal axis, before this was the x-axis, which has the equation y equals 0. But now that could be any value for k, so it's just y equals k. Before this was our y-axis, which has the equation x equals 0, but now we can use any value of h. And then foci, vertices, all of that gets shifted by h and k. The formula for finding our asymptotes, if you're using the kind of box method that I've just demonstrated, you can think about it as finding an equation of a line through the center and one corner of the box, the asymptote box. Being able to find the equation of a line is very important. Are we going to be doing that in this chapter? No. So if you can sketch the asymptotes, you don't really need to know the equation of the asymptotes. However, being able to solve the equation of a line is a skill that you already have in your toolbox. Okay, so let's look at a couple last examples here. When we shift H and K, the shape of the hyperbola stays the same. We've got our center, and then we have our vertices, and then outside of that we have our foci, and whether it's horizontal or vertical, all we've done is really move the axes to a different place. So the procedure is going to be the same. We'd like to find the standard form of the equation for the hyperbola whose conjugate is the smaller one, so that's B, axis has endpoints at -1, 4, and 5, 4, and the transverse axis, that's the one with an A, has a length of 8. However, this is the whole axis, so A is half of 8. 8 over 2 is 4. I'm going to put it over here. A is 4. Then to find B, I need to know halfway between our 2 points is the center. -1, 4. Let me write that nicer. -1, 4. And 5, 4. Halfway between those will be 2, 4. 5 minus -1 over 2 is 3. 1, 2, 3. 1, 2, 3. That's going to be 2, 4. That's how I did that. Okay, so I'm going to sketch a picture. I've got -1, 4, and 1, 2, 3, 4, 5, 4. And then I've got my center. Those were the conjugate axis endpoints, so those are just going to be part of my box. Transverse axis has a length of 8, so that's 1, 2, 3, 4. 1, 2, 3, 4. Those are my vertices. Um, 2, 4, 5, it should go there. There are my asymptotes. There is my hyperbola. A is 4, B is 3. In order to find the equation, we don't need to find C. I know that C, the foci, would be kind of outside here. Okay, so by drawing the picture, I'm able to see that this is an up and down opening hyperbola. So that means that my y is going to go first. So I have y squared over something minus x squared over something equals 1. In my y direction, my distance here was 4 squared. In my x direction, my distance was 3 squared. So I have y squared over 16 minus x squared over 9 equals 1. Okay. And our last example, locating the key points of a hyperbola. Find the center, vertices, and foci of the hyperbola. So first thing, the center is HK. So x minus h, y minus k. Negative h is 1, so h is -1. Negative k is 0, so k is 0. So we know that the center is at -1, 0. Vertices, that comes from A. A squared is 4, then A is 2. So if I say this is in the x direction, so for the x, I'm going to do plus or minus 2. Vertices, -1 plus 2 is 1, 0. -1 minus 2 is -3, 0. Foci is going to be C, so I need C squared equals A squared plus B squared. A squared is 4, B squared is 9, so that C value is the square root of 13. So now I'm going to take foci, -1 plus or minus the square root of 13, 0. I'm going to rewrite those separately. -1 plus the square root of 13, 0. -1 minus the square root of 13, 0, so that we can see that they're 2 different points. Okay, so we have our center. our vertices and our foci. If that's hard for you to follow because I didn't draw a picture, that just enforces the fact that you should be drawing a picture every time. So let's look at the picture. I'm going to start by saying x minus 1, so h, or x plus 1, so h is -1. K is 0, so there's my center. I go in the x direction, the square root of 4, so that's 2 in the x direction. And then y, I have over 9, so the square root of 9 is 3, so it's 1, 2, 3 up and 3 down. There's my box. There are my asymptotes. X goes first, so my vertices go on my x direction. There is my hyperbola. So the center was -1, 0. My vertices are 1, 0 and -3, 0 confirmed here. And then the foci should be just outside of that by a distance of c, which we calculated. And that's how we can see that it is a distance of -1 plus and minus the square root of 13. The distance from the center to the foci is the square root of 13 units in both directions. Okay, if you have questions, always feel free to email me. We will do some more practice in class.